Hello and welcome to episode number 20 of CS350 Online. I'm your host as always, Leslie Asted, and in today's episode we are going to start another new topic, which is the wonderful topic of file systems. Exciting. Before we get into that, if you're following along with the textbook, the relevant reading would be the one on files and directories. And again, I just want to remind you of the reading assignments and quizzes that are on Learn. I was looking on Learn here the other day, and let me just log in. Of course, it's probably going to not let me because, you know, Duo and all that, but okay, let's see here. So looking at our quizzes, it looks like a very few of you have actually completed any of the quizzes, so less than half of the class. And the reason why I keep bringing it up is I don't want it to reach the very end of the term, which we are approaching in just a few short weeks. And then you find out, oh, I've got all these quizzes to do, and you get in a panic. So the reason why I keep bringing it up is just so that you are very aware of what's going on. And again, for the reading assignments, don't forget, they are available only for about, a 7 to 10 day period of time. So make sure that you actually get them done on time. The next reading assignment is available on July 23rd, so that will be the end of this week, I think, and is due on July 30th, and that one is on file systems. In particular, it's the paper about the log structured file system, which is a very popular format of file system, and we'll talk more about that type of file systems another day, so just don't forget that. And then for those of you wondering about what your final assessment / final exam are going to be, it's an online assessment just like all of the other ones have been. It's a quiz on Learn, and we are just asking that you take some time to do it. And you will see immediately your score. You get a couple different attempts at it. Each time you write it, it's going to be a little bit different. And it becomes available, just so you know, on August 7th, and it will be out of commission on August 16th. So you've got about a week to just less than 10 days to actually do it. The reason why we're giving you such a large period of time to actually try your final assessment is in these times where everything is online or some model of hybrid / online, there's no real final exam schedule, and I didn't want to set a date and then have that coincide with an exam date that you would have from one of your other classes. So we're giving you these 9 days to choose when you do the final assessment so that you can do it on your own time, when you're well and studied for it, and when you are when it's not going to overlap with any of your other courses, because we don't want you to be that stressed, right? There's enough stresses in the world right now. All right. So, our OS of the day then. We have finally, at episode 20, reached Windows. Now, I'm going to assume that this is an operating system that every single one of you has actually used before. I'm sure there are some people in the world who have never touched Windows before, but that's not the majority of people. Now, Windows was released very shortly after Apple OS, so it was released in 1985, whereas Apple was 1984. And as we all know, Windows was actually written by Microsoft. And just like Apple's operating system, there are two distinct classifications of their OS. There is the DOS-based OS, and then there's the not DOS-based OS. And we are currently on a not DOS-based OS. But the DOS-based OSs, which I've listed actually on this slide here, go from Windows 1, which was released in 85, all the way to Windows Millennium Edition, also known as ME. And that was released, I want to say early, or 99, 2000. I don't actually know. It's one of the versions of Windows that I've never used yet. It was released in 2000. It was not one that people were generally happy with. And that's kind of one of the interesting things about Windows, is that there's been versions where people were really, really happy with it. We love this version. It works really well. It does what we want. It's got bugs, but we can deal with them. And then there's been other versions that get released and they're epically bad and everybody hates them. That's life, I guess. Windows 1, however, was really created to compete with Mac OS. It's just an extension to DOS. So it's not something like when you turn on your computer and it boots, it doesn't like boot right into Windows. You usually had to start it manually. And that was pretty true up through Windows 3.1. Although you could have it auto boot into Windows 3.1, I want to say about 50% of machines you actually had to manually start Windows from DOS. Now, this Windows 1 was incredibly limited. It didn't really have any kind of multitasking for the user programs, except for that which was used for the messaging loop for the user interface, so that you could actually send signals to the correct windows. The graphics environments was really, really simple. You couldn't have overlapping windows. Everything had to be tiled with the exception of the about screen, which was actually allowed to be tiled, but it didn't have a lot of interactive capabilities, so that worked out. So it was very, very simple, and it looks nothing like what you know of today. And there was a Windows 2, and it wasn't that popular. I can't remember which was the first Windows I used. I'm not sure if it was 1 or 2. I want to say it was probably Windows 2, which was very, very similar to Windows 1. But again, you're asking me to remember something from like 30 years ago, so I don't remember that well. I do, however, remember using Windows 3.1, which is probably my favorite version of Windows. I don't know why, it just is. Maybe it's the nostalgia. It's the last of the 16-bit operating systems offered by Microsoft. So that means that, yes, Windows 1 and Windows 2 were also 16 bits. So 16 bits means you do not actually have access to that much physical memory because your addresses are only 16 bits long. So yeah, that means you have 2 to the power of 16 bytes of memory. So I think that works out to be about... I don't remember, but I want to say it's probably like 64 megs or something. It's not a lot. But to be fair, if you look at how much memory systems had between Windows 1 and Windows 3.1, it wasn't very much. My Windows 3.1 machine had 30 megs of RAM. And my machines that came before that might have had 1 or significantly less than 1. So 16-bit addressing really wasn't an issue at the time for a consumer system. And that's the thing you have to keep in mind, is that Windows wasn't really meant to be used for commercial operations. So this is not a multi-user operating system. It does not support any kind of multitasking to start with. It's really meant for desktop office use, and that's really about it. Now, Windows 3.1, which was exceptionally popular, like it was everywhere, it worked pretty well, but the concept of multitasking didn't really happen, I want to say. I mean, you could open several things at the same time, but it was kind of weird, and it just didn't make sense because you didn't have a lot of screen real estate. So like, I know when I have a lot of programs open, I have them actually like side by side, and that works because I have a 38-inch ultra-wide monitor, so I can literally, it's like having 2 4K screens in one. So I can actually have a full-sized Chrome window right beside like a full-size terminal, and that's really cool. But if you're looking at like the Windows 3.1 era, we're looking at like VGA graphics and SVGA graphics at best. And so you're looking at a screen resolution, maybe if you're lucky, of like 640 by 480. So being able to actually see things nicely, you didn't tile things so much. However, Windows 3.1 did actually support cooperative multitasking. So if you remember, that does give us the ability to have multiple programs running at the same time, the illusion that they're running at the same time. But in reality, the only way that the context switches will actually occur is if a thread is going to terminate, if a thread voluntarily blocks, or if a thread actually calls yields. And if you don't yield, there's no preemption, and so there won't actually be any concurrency going on. So, of course, nobody also wrote programs like that back then, so even though it was supported, I wouldn't say it was really a big feature at the time. Now, what's really interesting is even though Windows 3.1 and 3.11 were long since deprecated, these two operating systems actually, you'll still see them around. I mean, I have a VM of Windows 3.1 because it's fun to play Windows 3.1 games inside of Windows 3.1 for old time's sakes. But where you actually still see this is Windows 3.1 is actually really tiny. So I remember installing it. It's 4 or 5 floppy disks, 3.5-inch floppies, and each of those is 1.44 megs. So you're looking at like less than 10 megabytes in the install. So it's like maybe 6 or 7. It's really small, which means that it's great for embedded systems. And so where you see Windows 3.1 today is actually airplane entertainment systems and POS devices. Yeah. If you're ever wondering why airplane seatback entertainment may not be the best operating system, it's because it might be using an operating system from, 30 years ago. Oh, well. Now, Windows 3.1 was followed by Windows 95, which I'm sure many of you have heard of. And then, of course, Windows 98. Now, they made a really big deal about releasing Windows 95 because it made a huge change in the user interface to something that you're probably more accustomed to. But Windows 95 was incredibly buggy, and a lot of that came down to driver support, hardware support. Most people didn't have enough hardware support for it, so it was really, really slow and really buggy. Blue screen of death plagued was Windows 95's, I want to say, motto. And then Windows 98 came out a couple of years later and was a huge improvement to Windows 95, and I think a lot of people used 98 for quite a while. I know I did, actually. And then, of course, Windows ME came out, and it was another kind of epic failure. People didn't like it. It was very, very buggy. But these are the DOS-based Windows, so they're still sitting on top of DOS. So whatever restrictions DOS has, you know that those restrictions are going to be carried forward into the desktop environment. So still very limited. You're still doing cooperative concurrency. They were using 32-bit addressing, and that was okay for 2000 because most people didn't have more than 4 gigs of RAM. Most people had about, the computer I bought, the top of the line machine I bought in 2000, I think had 512 megs of RAM. So we weren't at the limits of physical addressing at that point. And I mean, there were a lot of other restrictions. So DOS, again, has a really restricted file system. So we're still looking at Windows that's using a FAT-based file system, which had a lot of restrictions on file names. So it had like 8-character file names with a 3-character extension. Files actually couldn't be too large. And in fact, the FAT file system, FAT32, which is what these ones would have used by default, 95 through ME, they actually have a file size limit of 4 gigs. And FAT16 had an even a much smaller file size limit. But again, it wasn't a big deal. This seems like a huge deal to us today simply because we're using 64-bit addressing and, files are really big. Like if you want to go download a movie legally, you might be downloading something that's anywhere from 20 gigabytes to 260 or 80, depending, did you get the Lord of the Rings theatrical release or did you get the Lord of the Rings super extended, awesome, I don't know, whatever edition that's got 6 hours of extra footage in it? It's always the movie you pick because most extended editions only have like 7 or 8 minutes, not like hours of extra content. Anyways. So this back in the restrictions weren't that big of a deal, I want to say. What's interesting, though, is at the same time that these were the consumer versions of Windows were being released, there was actually commercial ones as well. And the commercial releases are a completely different OS build. They are not based on DOS whatsoever. They are separate entities. And they actually used to be known as the NT family. And that started in 1993. They have proper 32 and 64-bit support. They have virtual addressing. They have preemptive concurrency. and all of the things that we would expect from an operating system in that time. So the NT family, and that's actually what you are using today. So the NT family, so there's like NT1, NT2, NT3, and I think NT4. I'm trying to remember things from like the 90s, and that's a long time ago. So, and then of course Windows 2000, which came right around the same time as Windows ME, was actually the first, I want to say, NT version of Windows that consumers actually had access to. And again, it was a lot more reliable and a lot more capable because it wasn't built on top of DOS. Now, they still look like they have DOS access, because you can open cmd.exe, so command.exe, and it looks like DOS and it behaves like DOS, but it's actually just DOS in an emulator. They actually have a much, their terminal actually supports a lot more than DOS actually would. So the NT family was the first to use 32-bit virtual addressing. They used paged memory, virtual memory, whereas Windows 3.1 actually used segmentation. The fragmentation horror, and yet it wasn't a big deal. And the reason why segmentation actually worked with Windows 3.1 is because we weren't really running multiple things at the same time, so it didn't matter. Anyways, this family is a much more modern kind of operating system. And from 2000, of course, we went to XP, which was pretty popular. Vista, not so much. And then Windows 7 was massively popular. 8, 8.1, and 9, not so much. And now, of course, we're all on Windows 10. And, well, I guess they've actually just announced in the last week or two that Windows 11 is coming. And, I'm curious to see when is Windows 11's. Let's see when Windows 11 is going to come out. They say this year. Oh, they're saying October. So you only have to wait a few more months to try a new version of Microsoft Windows. Or something. I don't know. To be quite honest, I don't really use Windows machines anymore. I haven't used them in a long time because they're not so development friendly. Now, one of the interesting things that's happened is in the last 4 or 5 years, Microsoft's really realized that to get the full support, I want to say, of the development community, you've really got to start supporting the Linux GPL new compiling tools, or just that world, bash, and a proper shell. And so now we're actually seeing a lot of support for that kind of technology actually inside Windows. And my husband and I talk about this a fair bit. They're even getting support for X Windows and stuff inside of Microsoft, native X Windows, which is cool. But I'm sitting here and I'm thinking, how long is it, at the rate they're going and how much they're actually trying to integrate elements of Linux and GPL programs into Windows, how long is it going to be before Microsoft Windows is actually just another branch of Linux? That'd be kind of neat. Anyways. All right. So that's Windows. A couple pictures in, because everybody likes pictures. I know this one is all grainy and blocky, especially at 4K, but I took a screenshot that was 320 by 240 and I blew it up so it would fit. This is Windows 1. And this is the only overlapping window that you'll actually see, and that's just the entryway. You'll see everything else is actually tiled. And it does not look anything like Windows that you've probably ever seen. There's no start menu down in the bottom. And in fact, that start menu didn't actually appear until Windows 95. So here is Windows 3.1, and essentially in this gray area, which was usually tiled with some GeoCities-esque silly textured tile thingy, you would actually have a bunch of folders, and you would open on the desktop, and you open the folder, and it opens up one of these windows here, and it lists all the programs that are contained in that folder. But there, again, Windows 3.1 does not have a start menu. There's no start menu at all. There's just folders on a desktop. And you could have multiple things open at the same time, but they weren't doing preemptive concurrency, so you couldn't really watch a video and play Minesweeper at the same time. That just wouldn't work. Also because the computing power of a machine running Windows 3.1 was pretty bad too. Like you're looking at like 33 megahertz or 66 megahertz. Really, really low. And then, of course, everybody knows, or most people know, what Windows 10 looks like today. I know this is a low-resolution image. Sorry, I don't have a native one to show you. But you've got a Start menu, and you've got, you know, search bars for whatever that Cortana thing is that's really annoying that I disable immediately. And then you've got, you know, some stuff in this other corner here. And I mean, Windows 95 is where this kind of look and feel came from. But what's interesting is about Windows 8 through Windows 10, because they wanted to push tablets, they actually have two UIs. So this is kind of the traditional desktop UI. And then there's also a Metro UI, which is meant for tablet use. And that's one of my biggest complaints of the recent versions of Windows is some settings you have to change through like the Metro path, and other ones you have to go through the desktop path, and it's just really confusing to find the setting you want to change in the right spot. I find it really chaotic having the two different UIs. Personal take on things. All right, anyways, that was a long rant about Windows, but hey. So then, let's move on to talking about file systems. So this is the last major topic of the course. We do have one topic after this that's like one episode, and that's virtual machines. And then depending on how much time we have left, we'll probably talk about networking in the OS and then designing your own operating system. But let's talk today just about the file systems. So when we're thinking about file systems, one of the things you have to ask is, you know, what is a file system? And if you were to actually go and try to get a definition of a file system, it's hard to, it's not a single thing. A file system is actually a whole bunch of data structures and algorithms that we are using to store files, retrieve and access files, and perform checks on those files. And I mean, file systems are very, very important because what we need to do is we have all of this data, file data, like your assignments, like things you've downloaded off the internet. Maybe you've decided to download Mint, for example. Then you need to store that file on your disk. And when you turn the computer off and then you turn it back on again, you want that file to still be there. So files are these persistent objects, and we need them to stick around. That's what persistent means, of course. So not only do we need them to stick around, we need to be able to find and retrieve them and modify them at a future date. So file systems are all of those data structures related to how do we make sure that data is stored persistently, but how do I make sure that once it is stored on the disk, that I can actually retrieve it at some future date. So we have to be able to find the file, we have to be able to modify the file, and we have to be able to remove it, and so on and so forth. And if we were to look at file systems, there's actually, what's interesting is it's divided into different layers, where some of the layers are actually optional. So non-optional layer is the logical file system. And this is the high-level API. This is what you have used. This top level, that is what you are using when you open a file, when you read a file, when you write a file, when you modify the permissions on a file. All of that is part of the logical file system. And this is really an abstraction of what's happening underneath. The nice thing about a logical file system is when you're opening a file, you don't have to worry about how the file is stored underneath. For example, I'll open up this. So this is Dolphin. And so this is my, my home directory. I've got a bunch of data. I have network drives as well. Looks like I haven't actually logged into them yet. But I don't need to do something special to open something off my network. I haven't set it up here yet. So, I mean, unless I actually need to physically connect to it. So I have a NAS, and in order to actually connect to my NAS, I actually need to type in the IP address, and I need to put in my username and password. But then once I've done that, it's as simple as just clicking on it and accessing it in the exact same way that my native disk would be used. And I don't need to worry about the fact that the system here is using ext4 and I don't know what file system my NAS is using. Okay, I do technically know, and it's also ext4. But the point I'm trying to make is from this file explorer, I don't need to know how that data is stored on the disk, and I don't even really need to know what disk it's on. That is the logical file system completely abstracting everything that's underneath so that you don't have to worry about it. Because think about this, when you are opening a file in like C or C++ and you're writing to it, do you have to tell it, oh, and this is on an NTFS file system, and oh, this other file's on a FAT32 file system? Do you have to use separate functions? No, you're not even aware that there is these things called file systems underneath. You just open the file, write to it, and close it, and that's it. And that is the logical file system completely abstracting the implementation from you. And that's a really good thing because it makes life easy, right? All right. Now, sitting under the logical file system is something called the virtual file system. Sorry, I was just looking up here because I could show you how the virtual file system plays a role if I could find a disk, but I can't see any disks up there. I have a multi-tier desk here, and above me is a shelf with a bunch of electronics on it, but I'm pretty sure my disks are buried in a box at the back, so we can't do that. But what the virtual file system does is it takes all of the lower level physical devices that are file systems. Ooh, that's some nice autofocus. Yee, a ghost. It's too much fun. Anyways, I'm going to take all of the lower level file systems and I'm going to present them to the logical file system as one thing. So that's super useful. So I'm trying to get this camera to autofocus and it doesn't want to. So I look like some kind of creepy ghosty thing, which is kind of cool, I suppose, but let's see. Let's get it to... Come on, camera. There we go. Okay. Sometimes when your camera won't autofocus, it gets in a funny state. You have to put your hand right up to it. So it's like, oh, wait, my focus has changed. And then slowly pull the object back away from it so it'll track it. Kind of works. All right, so we've got the virtual file system, which is going to take all of the different disks plugged into your computer and present them to the logical file system as one unified thing. And you've done this before, you've used this feature before, because if you've ever plugged an external drive into your computer and then opened up File Explorer or Dolphin or whatever the heck it's called in macOS, you'll see that it's been plugged in and you can now access it, but you access it the exact same way you access everything else. And that is the virtual file system presenting that to the logical file system, all those different disks as one cohesive unit. We'll talk about how that actually works later. And then sitting underneath, you don't, by the way, have to have a virtual file system. You don't have to do that. And then sitting underneath of that is the physical file system. And the physical file system is how we are actually storing the data on the physical disk itself. And it's funny because when we think of file systems, we never think about logical or virtual file system. We're always thinking of the physical file system. So you've heard me say NTFS, and you've heard me say ext4, and you've heard me say FAT32. Those are actually physical file systems. Those are different algorithms and methods that we use to store the data physically on the disk. And there are many different physical file systems out there. So if you are using any kind of Linux kernel-based file system or Linux kernel-based operating system, you are probably using ext4, which is a journal file system, and like before ext4, ext3 was super popular. And the one that I used before ext4 was actually RiserFS, which was one of the first journaled file systems for that platform. Unfortunately, the person who created it also is a murderer, so that file system fell out of popularity pretty quick. But it was, you know, at the time, it was actually a really good file system if you could get it to work. And my understanding is a lot of the really good elements of RiserFS have actually made their way into ext4, which is kind of cool. And then, so that's if you're like using a Linux-based system. If you're on a Mac OS and you have a really old Mac with not an SSD, you're using HPFS or HPFS Plus. And then if you have one with an SSD, you're using APFS. And if you are using Windows, of course, you're using NTFS, which is their version of a journaled file system. So when we think about file systems, we're usually referring to the physical one and not these upper ones. We're not going to go into physical file systems today. That will be another day. So today we're going to start with just the logical file system. So as I said, the logical file system is all of the high-level API functions that are abstracting the lower levels of the file system from the user. So that's things like opening a file, closing a file, reading, writing, seeking, and then modifying any of the metadata associated with the file. So that's pretty cool. Now, a lot actually happens when you do these that you're not even aware of. So for example, when you open a file, what does open actually do? Why do you have to physically open it? Well, we have to find the file first. And that's what open's going to do, is it's going to find the file, and it's going to do things like check permissions, because you do not have permission to read and write every file on your disk. And so we're going to actually have to find the file and then read the metadata in to ask, does this user have permission to do this thing with this file? So do you have permission to read this file? Do you have permission to write this file? And if you do, then what happens is open returns to you a file descriptor. And that is how you refer to the file everywhere afterwards in that program. And the reason why we're going to do that is because nobody wants to have to convert the path of the file, the string, and do a string-based search every time I want to access the file. So the file descriptor is more like an integer, so we can do like a nice integer lookup in the future. Now, we do a bit more with inside of open. Once we get the file identifier or the file descriptor, we're going to put that into the processes open file table. And that it's also, so we're going to have a file descriptor, and it's going to say this process has this file open, and it's also going to indicate what is your current position in the file. And if you've just opened the file, of course, your current position is byte 0 because you haven't read or written anything. And then one other thing we're going to do with open is we're also going to notify the kernel this process has this file open. And so in the open file table in the kernel, we're also going to increment the counter for that file. And you've actually probably been on the bad side of that counter if you've ever had a little USB device in Windows, and you go to safely eject, and it's like, no, I can't, somebody's still using it. And you're like, but I've closed all my programs. And it's because the open file table in Windows still thinks that there's a process that has it open. And so it's therefore not safe to eject it yet. So it's really important that you actually close these things properly. All right. Then we have close. Now, what's interesting is this is a function for file systems that so many people don't use. And I can't stress enough how important it is to close. So number one, when you close a file, you're actually doing several things. You're invalidating the file descriptor from within the process. So the process is going to remove that from the descriptor table. You're also telling the kernel that this process doesn't have this file open, and so it will decrement the counter, which comes into play when you try to unmount something. You can't unmount it if somebody still has it open. And close also does some other things that aren't really mentioned in the slides. One of the interesting things about file systems is that you think of when I write to a file, that write happens right now. Not usually, actually. In reality, what happens is writes get cached. And then periodically, the cached writes, cached to memory, periodically those writes will then dump to the disk. So they might get grouped together into a bigger block of writes, and then the bigger block of writes will go to disk. Yeah, if you close a file, if you close the file properly, it flushes all of those writes to the disk. If you just shut the program down without closing the file, some of those writes will not get flushed. And then you open your file and realize a bunch of data is missing at the end. Oops. I've had this happen. I've seen this happen. This is a very real thing, is that writes get cached. Now, I haven't seen it a lot with SSDs, but I do see it a fair bit with non-SSD devices. Now, where I have seen it with SSD devices is USB ones that you plug in, like little flash keys. And the other thing that can trigger the buffer to flush is actually the unmount process, which is another reason why, so if you haven't clued in, it's really important to unmount your disk properly before you unplug it. Number one, because it's good for the disk, but number two, because if you have any cached writes that haven't been flushed to the disk yet, when you actually perform that unmount operation, you are going to force those unflushed writes to actually go to the disk. And if you don't unmount properly, then those writes will get lost. So if you've ever actually hit the unmount button and it takes a little bit of time and you see the disk working away, it's flushing all those lost writes. It's really important you unmount your disk, and it's really important for you to actually close the file to make sure any unflushed data actually gets flushed to the disk. And then we have operations read and write. Now, you know what these do. They read from the file and they write from the file. But what's really interesting about reads and writes is we never actually tell the read and write functions where to do the read from or where to do the write from. They somehow magically have a start location. You just tell them how many bytes you want to read or write. Now, why do you not have to tell them where to do the read or write from? Well, because if you remember, I said in the file descriptor table of the process, we keep track of our current position in the file. And reads and writes are sequential from the current position in the file. So if you do a read at 512 bytes immediately after opening the file, then you just read the first 512 bytes of the file. And after the read, the current position in the file is going to be 512 bytes in. And then if you do a write of 100 bytes, you are writing from 512 to 612. And you've advanced the position of the file to 612. Now, what if you wanted to do random reads and writes? Well, that's what the seek operation is for. So seek actually doesn't touch the disk, and it's important to note that. But what seek is going to do is seek is actually going to modify this file descriptor in the file descriptor table of the process to give it a different start position. Okay, so that's what it's actually doing. And that will let you read or write from a random position in the file. Now, one word of warning about this, if you actually read the man pages for seek and lseek, you'll note that they don't actually validate the byte that you're moving to, and it may not actually be in the file, which means that you could seek way beyond the end of the file and then try to read from it, and you wouldn't get the error on the seek, but you would get the error when you tried to do the subsequent read. Then we've got a bunch of functions to modify the metadata of the file. And you're like, what do you mean by metadata? Well, let's take a look. Okay. I don't think you guys want to see my machine learning stuff. Let's open a new tab. There we go. Let's make this font a little bit bigger. Okay. So here we go. We are at my home directory. And what I'm going to do is I'm going to do ls-la. And that is actually going to show us a lot of the different metadata associated with these files. So what you can see here is we've got the owner of the file, and we've got like the group. Sometimes it's creator and owner. And then we list the file size in bytes. We have usually here that this might be the creation date or the last edit date. And then we've got information on the far left that actually indicates the permissions. This is all metadata that's associated with the file that tells us when was the file created, how big is the file, who's allowed to open it and modify it, and who's allowed to execute it. And we can change these things. So for example, I'm going to create a file. And if I look at the permissions of the file I just created, you'll see, so it's the first, this is user, and this is group, and then this is others. So anyone, this user can read and write the file. Anyone in the same group as this user can read and write the file, but everybody else can only read this file. So if I want to change the permissions on this, now there's actually two ways to use chmod. Chmod is going to change the permissions. You can use a numerical code, but I can never remember the codes. Or you can do it very simple. Let's say I wanted to give everybody execute permissions, because I don't know why you'd want execute permissions on a text file. I would do UGO, user group other, plus X, and then example.txt. And now you can see here that user, group, and other all have execute permissions for this file. Now, obviously, I don't want this text file to have that, so I'm now going to remove. So user, group, other, minus X. There you go. I took away its execute permissions. Again, there are numeric codes that you can do this with as well, but I don't remember them. I think 777 is the only one I remember, and that gives everybody access to everything, which I don't want. Now here's another little quirk. So we can change things like the permissions, but what's really interesting is that we can change some other stuff as well. For example, let's suppose that you are on co-op and there was a task you were supposed to do at the very beginning of the term and you forgot to do it. Oops. That happens, right? You forget to do a task. But your boss never actually says anything about it until, 2 weeks before the end of the term. And they're like, hey, where's that thing I asked you to do? I asked you to write me a document for, to tell me how to use, I don't know, scikit-learn or something. And you're like, oh, I forgot to do that. But you don't want to tell your boss, right? You never want to tell your boss that. Because it's right when you're going to get your co-op evaluation. You want to make your boss look like the one who forgot it. Well, there's a way to do that. So the problem is, if you do the task right now, like you stay up, pull an all-nighter, which you should never do, but if you pulled an all-nighter and you did the task, and then you submitted it, the timestamp on the file would be very clear that you did it just now, and you were only doing it just now. And maybe your boss doesn't care, but maybe your boss also looks at you like, seriously, I asked you to do this like months ago. And then they're going to give you like a good instead of like an excellent or something. So how do you make it seem like you did it when your boss originally asked and your boss just lost it? Well, you send them an email saying, oh, really? I sent you an email with this, on such and such a date. Maybe it didn't send properly. Maybe you didn't get it. Here's another copy just in case. But the problem, of course, is if you send them another copy just in case, it's still got that timestamp indicating you did it last night. So what we really need to do is send that email, but send them a file with a timestamp that's been modified. And you can do this. It's very easy. So as you can see here, example.txt was created on July 20th at 12:04. Maybe this was your co-op term, so maybe you were supposed to do this in May. So we can actually change the time on this file. So we're going to do touch again. MT. Now the month, let's see, this is the, I don't know, month. I guess May is the 5th month. So let's do 05, and then let's say it was supposed to be due on the 12th. You wanted to do it really early in the term. And then here's the thing, you've got to choose a time. You don't want it to look like it was done late at night, because if it was done late at night, that makes it look like you're not good at time management. And you don't want it to be done really early in the morning either, because then it looks like you stayed up all night. So it's got to be done in a very reasonable amount of time. So then let's say that we finish this at 2 o'clock in the afternoon. And if it's a multiple of 5, it's going to look too fishy. So let's say 2:43. And then we look at that again, and we see that example.txt was now created on May 12th at 2:43 p.m. And you send that to your co-op boss, and you make them think they're going crazy instead of you just not doing it. All right. Don't do that. Seriously, I see some of you on Twitch saying, I'm so going to do that to my future boss. Don't do it. Unless your boss likes pranks. Yes, I've had co-op jobs, if you're wondering, where pranking was quite a fun thing. It was actually Google. The one group I worked at Google was pretty big on pranks. And yeah, we had a bit of fun with that. So a question on Twitch is there a way to catch that if you're the boss? Not really. I mean, there might be ways that I'm not aware of, but I do not know of any way to catch that. But this is actually a thing. So you might have noticed in your CS courses that we don't accept timestamps as proof you did something on time. And the reason is exactly what you see here. We can change it trivially. And this has been a rule since like I was an undergrad, where it's like if the submission system wasn't working and you sent them an email afterward and you're like, here's a screenshot showing you my timestamps, and you can look at my timestamps on my files and see that I haven't changed them since the deadline. That won't generally get accepted because the timestamps are so easy to change. And so generally speaking, the only thing that we'll even consider accepting is proof from some kind of source control repo showing like branches and stuff like that, like the actual dates on submissions in branches, which isn't to say that that can't be forged either, but it's a little bit harder to do. But yeah. Yeah, no, I want to say most people in CS know about this trick, most of the profs, and that's why we don't accept timestamps. Now, of course, if you're working at a company and it's all like Windows machines or something, maybe they're not familiar with this particular little trick. So maybe you can get away with it. But you really shouldn't. Just do work on time. All right. So we've already talked about this slide, so I'm going to skip it. And now I'd actually like to do a little example. And I got to fire up my Bluetooth device here. And then let's open up. Okay, there it is. Okay. Oh, helps to use the right end of the pen. So what we've got here on the slide is a little snippet of code. And this is going to show you how sequential reading actually works for a file. So we open the file, and you'll see we're opening it read only. And that's just saying I don't want to write to the file. Typically, when you actually open a file, you have to indicate how you want to use the file, and that goes down to the permissions check. You might be allowed to read a file, but you might not be allowed to write a file. So you need to specify how you're using the file, because that's going to play a role in permissions checking. So in this case, we're opening a file read-only, and then we are going to read from the file 512 bytes at a time. So what would happen is if my file contained the following. I apologize for the messy writing. It is a little bit weird using one of these pens sometimes. So instead of 512 bytes, if we were to just read 3 bytes at a time, this is how the file would be read. We would read this first, and then this second, and the third. So we are doing sequential reads and writes. At the end of each read, the pointer or our position in the file has advanced so that the next read takes place at the next position. All right. Now, we can combine this with the use of seek, or lseek in this case, which is just another seek. And we can try to read from the file in a different order. And all we're doing is in the file descriptor table, we're indicating a different start point. So in this particular case, we are going to move the pointer to the last 512 bytes, and then we'll read that. And then in the next iteration, we're going to move it to the last 2 blocks of 512 bytes. So we're going to read the file backwards 512 bytes at a time. So if we were to do that with our similar example here, let's open this up a little bit. Use maybe a different color. So if we have the same file contents, and we read it 3 bytes at a time. In the second example, we would actually be reading these 3 bytes, these 3 bytes, and then finally ABC. So our file pointer starts here, that's the first, and then the file pointer gets moved there, and that's the second. And then at the very end, we're not going to move it again. So there you go. You use the seek operation to change where we're going to start the read or write from. Now, again, the thing I really want to stress is that the seek operation does not actually look at the file itself. It's only modifying the file descriptor table entry for the process, and it's simply changing the current position in the file. It does not check if the position you have set it to is valid, and this is not just something that's true of OS 161. This is actually straight out of the lseek command page for the Linux kernel. Okay, so this is very much the behavior of lseek in the real world, is that it doesn't validate the position of the file. So it doesn't return an error if you've moved it to an invalid position, but the next read or write will return an error. So keep that in mind. All right. So you've seen kind of the high-level functions that you're used to for reading and writing files, changing various attributes about those files. But the one kind of thing we haven't really talked about is, what is a directory exactly? And what's interesting is, I mean, when we think about directories, we're almost always thinking about it in this pictorial sense of, oh, look, this is your videos folder. And it's an organizational mechanism such that inside of the videos folder, looky here, there's a bunch of videos. This is where all my live stream dumps go. Which is why you see one that might be actively changing in size right now, because that's what we're recording right now. But the point I'm trying to make is that this is what we think of folders as being. It's an organizational tool. And to be truthful, that is how most people use them, is it's an organizational tool for a human so that you can actually find your stuff on your disk. I know when I was young, everything went either onto the desktop or into the documents folder. And I know my mom, everything goes onto her desktop. There's no concept of organization into like a hierarchical structure. Obviously now that I do a lot of work and research in CS, I organize things as best I can. But a lot of people don't. But that's actually not really what, I mean, directories do obviously help users with organization, but they're more than that. They're how the computer actually finds your file. That path that you give is actually the path we have to take through the file system to find the actual physical file. And directories, what they are actually doing is they are mapping the file names that they contain to numbers. Because inside of the kernel of the operating system, inside of a file system, do you honestly think we want to be doing string comparisons and string lookups all the time? Of course not, because those are so inefficient. We really want to just be doing integer matching and integer comparisons because they're so much cheaper. And so what directories actually do is they map every file name to a number. And within your file system, every single file is actually internally referred to by a unique identifying I-number as opposed to its actual name. And then the directory is mapping the names to numbers. So that's pretty cool. And what happens when you open a file and you present it with a path is we're going to go into the root directory and we are going to look for entry home, and it's going to give us the I number of home. And then we can find the file with that I number and open it up, realizing it's a directory, and then find within it the I number for directory user. So this path through these directories is going to help us map our path through our file system to get the I number of the actual file. And if you were to draw this out, it actually creates a tree, a beautiful tree. And we call this the hierarchical namespace tree, or just the namespace tree. And at the top, this is your root directory. And then these are the directories that are contained inside. And yes, you can see docs is mapped to I number 145 and foo is mapped to 24. Each thing is mapped to its own unique I number. And in the namespace tree, something I'd like to point out is that directories can be internal nodes or external nodes, so they can be on the inside of the tree or a leaf of the tree. But a true data file can only be a leaf. Files themselves cannot be internal. So just keep that in mind. But everyone has a unique identifying number. So that's pretty cool. And when you open a file and you pass it a path, what we're doing is we are using the strings to traverse this tree, find the file, and get its I number. Once we have its I number, we are going to refer to that file by its I number for the rest of the time we are using it. Because again, we don't want to have to do this path again. We don't want to deal with strings. Now, you can actually see this a little bit inside a Unix-based system. So if we do VI, and then let's do documents. So I know a lot of people are not big fans of VI. Oh, well. I've been using VI for a very long time, and I'm not about to apologize for that. So if we open up this is what we see is that directories are actually files themselves, but they're special files. Now, I don't actually have anything in my documents directory. So let's go into the videos directory because I know I have stuff in there. And you will actually see, you won't see the I numbers they're mapped to, but you will actually see the list of all the file names the directory contains. So the directories are actually files themselves, which contain the file name to I number mapping, even if you can't see the I numbers here. One thing I'll say is those directory files, they can only be opened read-only. You cannot modify a directory directly. If you want to change something about a directory, you need to use the proper commands to do it. So things like mkdir, rm, touch, things like that, because that's going to make sure that you don't mess up the file system. We don't want to accidentally change the I number for a file inside a directory, because if we do that, we might now have two files which are supposed to be completely different now have the same I number, and you're going to have a really bad time. You're going to lose data, and it's going to be nonsense. So we can't actually directly modify that file as a text file. You could only modify it through system calls where permissions are going to be checked and things are going to be done properly. Okay. Now, what's interesting is that this mapping between the name and the I number, there's actually a name for this. It's called a hard link. And that's associating the name with that number. And what's really interesting is you can actually make as many hard links to files as you want. So if we go into this one, you can actually see on the next slide where we have file 147 actually has two very different names, but it's the same file. So there's one hard link, docs.a.txt, and the second hard link is foo.my. These are the same file, and they have the same I, because they have the same I number. I'm trying to select just this number here, but it doesn't want to. So that's pretty neat. Now, why would you use hard links? Well, we would use hard links, let's say, if you didn't always want to type GCC-10.0-1 and you just wanted to type GCC. We use hard links for libraries and for many other things. They are different from soft links. So a hard link is actually just another mapping between a name and an I number. A soft link is something else, and we don't actually talk about soft links or in this course anymore, but a soft link is actually a file that contains the path to the actual file. So to actually get to the file that's pointed to by a soft link, you go through this namespace tree once to open the soft link file, and then you read the link inside of it, and then you go through the tree again to get the I number of that actual file. So it's a bit of an odd thing, and it's implemented slightly differently on different file systems. Now, there are some restrictions with hard links. We do permit as many hard links as you want to a file, but we do not permit multiple hard links to directories. And the reason is cycles. We don't want a cycle in this graph. Cycles are bad for this graph. Allow me to show you why. Actually, I don't want to write it. I am going to use VI. This is more fun. Okay, let's make this a little bit bigger here. So let's suppose we have directory foo, and it's 87. And inside directory foo, we have access to a file called w.txt. And let's say that file is 77. No, 71. And then let's suppose we also have directory bar, and that's, let's say, 90. And then inside directory bar, it's 90. Let's suppose we have a link F, and it maps to 87. Okay, so I've made a cycle. And now I want to ask you, what are all of the paths to file w.txt? So let's actually try to list them out here. So we have foo w.txt, we have foo bar w or f w.txt, foo bar f w.txt, so on. The problem with creating this little cycle with the directories is that we now have an infinite number of paths to w.txt. And that can be problematic, especially if you're trying to do some kind of system search, because you're going to literally follow every hard link and you're going to sit there and loop around forever. So they don't generally permit multiple hard links to directories. And I mean, you could permit it if it didn't create a cycle, but then you have to have cycle detection code in your file system. And do you want to have that? Is that cheap? Not usually. So there you go. We don't usually allow that. All right, I'm not saving that file. All right. Now, the hard links are going to be kept track of by the metadata as well, because we like to know how many different links to this particular file are there. And at some point, we're going to want the ability to unlink a file, that is, remove a hard link. And the idea being that if you are the last hard link to be removed, that means that we are actually going to delete that file. Okay? And so we can also remove links. and delete the file. Now, what does it mean to delete a file? That's an interesting thing. So when we think of delete a file, our brain immediately thinks we're deleting all of the file data. And I want to caution you away from having that mindset, because when you delete a file, that's not actually what happens. What actually happens when you delete a file is that there's no more hard links, so the mapping between the file name and the I number disappears. And the data blocks that the file, the actual place on disk where the file is stored, gets marked as free, but the data isn't actually released or deleted unless you explicitly say so. So like, for example, on Apple machines, there's this thing like called safe delete or safe remove, and that will actually delete the data itself. But if you don't do that, the data's still there, and you could technically get it if you tried hard enough. But usually deleting a file is just removing the ability to find it and marking the regions of the disk it was using as available, even though the data itself is still technically there. And actually, if you're ever doing like a format of your disk, there's options to do like a quick format or a low-level format. And especially if you're trying to sell your disk or sell your laptop, do the low-level format and do it like 10 times, especially if you have a mechanical drive. Because I think it takes 7 overwrites to fully remove the presence of the previous data or something. But if you just do a quick format, all it does is mark everything as free. It doesn't actually delete any data. It just literally marks the whole disk as free. So all the data is still there, and you can still get it if you really wanted to. If you do a low-level format, it marks the disk as free and actually clears it out. So keep that in mind. I mean, even then, this has gotten people into trouble before. Like the Canadian government's gotten in trouble for this before. Various companies have gotten in trouble for this before. They didn't actually properly destroy the disk before they threw it in the garbage bin out back. And as a result, somebody did a dumpster dive, they pulled the disks out, and they actually end up, oh, look, you just quick formatted that. Well, I can get past that and get all the data off real easy. So, I mean, really, when you want to destroy a disk, not only do you need to like don't quick format, do low level formats several times, but you should honestly shred it, like physically destroy it, because it's really the only way you can guarantee people can't get the data off of it. And I mean, think about all the stress relieving behavior you would get out of doing that anyways. It's like an Office Space at the very end. Oh, I suppose I shouldn't, but spoiler alert for Office Space. They smashed the printer to death with a baseball bat. It's funny. If you haven't seen that movie, you should watch that movie. There's some entertainment for the week for you. Go watch Office Space. I know it's an old movie. It's still a lot of fun. All right. So I think we're going to leave it here for today. And in our next episode, we're going to talk about the virtual file system. And then we are going to start talking about physical file systems, so how the data is actually stored on the disk. Because really all we've talked about so far is how to read and write, how to change the metadata, and how to actually find a file. But we haven't actually talked about how that's stored on a disk. So we will do that in our next episode on Thursday. So we will see you then.